Hello all, Namaskar. My name is Vijas Tiwari. Uh, MSc first semester, Department of Physics, Prithviraj Campus, Pokhara. Today I am going to give a short talk on the topic which entitled conservation theorems and symmetrical properties. First of all, we need to know about the term symmetry. Well, it has a long history. We do have a famous mathematician and a physicist, Noether, who gave us the true meaning of symmetry and related with the other known physical phenomena. She related the symmetry with other known conservation laws and give a most powerful and most elegant theory that we have ever have in the field of physics, and it has a wide application in every branches of physics, and it is even like the backbone of today's modern physics as well as quantum mechanics. Today, symmetry is a property by which a function or a system remains invariant under certain operation, and the system is said to possess symmetry under such operation. Every symmetry corresponds to conservation laws. This is the statement given by famous physicist Noether. As example, we will take a cylinder and rotate it about its by any any axis passing through about its axis and by an arbitrary angle, then its shape does not change, right? We all know that. And this property of cylinder is said to is rotational symmetry. And another example is a sphere. Sphere is considered as one of the most symmetrical object in the universe, and we have also encountered sphere in many physical phenomena, like we have considered electron shape as sphere, and it had made a very much easier explanation of electron in various fields, including the Millikan's well drop. And we have taken and if we consider the particle nature of electron, we consider that as a tiny point like spherical object, and this is because of its high symmetry. And as we know that symmetrical coordinate corresponds to cyclic coordinate, and such operation has no effect on the description of the system. This is already known from the definition. And any symmetric operation under arbitrary translation corresponds to linear momentum, and under arbitrary rotation about arbitrary axis corresponds to conservation of angular momentum, because about that axis the coordinate is said to be cyclic, and every cyclic coordinate corresponds to conservation laws that we have also proved, right? And today we are and the next slide is the conservation of linear momentum following the laws of symmetry. Here we denote a system whose whose generalized coordinate is denoted by qj, and we assume that this system is displaced along certain direction by an infinitesimal distance dqj. Then the Lagrange's equation of motion is given by the equation that we all have seen in the figure. And doing simple mathematics, that L is equal to T minus V, we have the next equation. And for conservative system, here we have limited our assumption approaches and have constrained to the conservative systems, where the kinetic energy is simply the function of velocity, and potential energy is simply the function of position. Then finally the above equation reduces to first derivative of momentum,
Excuse
which
me,
is
Vijay.
equal. Hello. Yes.
अलिफ हाफ भयो कि साथी अलिफ हाफ
Eh,
भयो हुँदो रहेन
okay. Here the rate of change of momentum is equal to the force, and this is the well-known second Newton's second laws of the motion. But we have to show that this component of the force this component of force must corresponds to the force along the direction of displacement, right? So it is sufficient to show that pj is the component of total linear momentum along the direction of motion, and qj is the component of total force along same direction for equation 1 to be the equation of motion of the system. The generalized force is, oh sorry, there is id that I need to write, is given by qj equal to summation I fi the partial derivative of position vector upon generalized coordinate. As we all know that uh, the law of transformation from the position vector to the generalized coordinate, we have already studied about those relations, and that the position vector is a function of generalized coordinate. Now it is obviously known fact that the change in the position vector actually corresponds to the change in the parameter, which is the generalized coordinate, right? But here we have to write the direction because position vector is itself a vector. So we assume that n is the unit vector along the direction of translation, and this equation number 2 is quite represented by the figure uh, alongside. Here qj is equal to the, oh sorry, I forget, there is a mistake that I forget to write fi in qj term. There is fi dot del ri by del qj in thus qj equal over here, so which is the component of total force along the direction of translation. Now the here we have substituted the value of n cap from the equation 2, and got got qj equal to nf, which represents the component of force along the direction of translation. Now we need to show that the generalized momentum, which is, now we show the generalized momentum pj equal to partial derivative of t upon the derivative of t with respect to its velocity. And doing simple mathematics, we obtain equation number 3, which even shows the component of p along the direction, which even shows the component of p along the n cap, and it is the component given by pj, sorry, given by pj. Thus these two, equation 2 and 3, suggest that the equation 1 is the actual equation of motion along the direction of translation. Thus now we remain to show that that the system is displaced through the coordinate qj, so we need to show that it is a cyclic. So no, we know it is a cyclic, therefore we need to show that the momentum corresponding to that coordinate must be conserved. Therefore is conserved and is constant, and is shown by equation number 4. Now we are going to prove the conservation of angular momentum using the symmetrical approach. The method is same. We consider a system with a generalized coordinate qj, and we represent the angular coordinate. This qj is the angular coordinate. Now we subject the angular displacement dqj. Then the torque is given by the first derivative of pj, and the qj is the torque, which is given by fi dot del ri by del qj. Here change in qj represent infinitesimal rotation of a vector keeping magnitude constant. What does it mean is that if we if we tie a rope in a stone and rotate it, forming a circle, then its direction changes at any instant, but its magnitude remains the same. The physics is same over here too, which is quite shown by figure given alongside. Here from the figure we clearly obtain that the magnitude of the change of the position vector is obviously is equal to the ri sin theta dqj. From here it is from here we can see that here the ri is the value ri sin theta dqj, and we need to substitute the value of del ri by del qj, and thus del r by del qj equal to ri sin theta. Then substituting these values, uh, and this is in magnitude form. Now in vector form we write it, here the n cap is the direction about which the system is displaced, the system is rotated, in fact. Therefore in vector form it is n cap cross ri, and now substituting the value, equation 6 to the equation 5, we finally get the n cap, here the fi dot n cap cross ri, and simple using properties of vector product, vector triple product, here we obtain that n cap dot n bar. Here n bar represents the total torque, and the dot product of n cap dot n represents the component of n vector along the direction of rotation, that is n bar. Thus this equation 7 represents that the qj is the component of the total torque along the direction of rotation. Now here we here we saw that the Pj also needs to be the component along the same direction, about the same direction, right? Which is the partial derivative of kinetic energy with respect to velocity. And substituting the values, we finally come to the and doing math, we come to the equation number 8, which shows the component Pj is the component of total angular momentum L bar about the direction and cap. Thus, the equation, thus, thus this shows that the partial derivative of that the first derivative of Pj is equal to Qj, which is the equation of motion of the system under rotation. Now, now it remains to show that the Pz needs to be constant. Pz needs to be constant because under the effect of generalized coordinate, which represents the angular part, if that is symmetry, then that must represent the cyclic, and the corresponding momentum needs to be conserved. Then del L by del Qj equal to 0. Now this second equation, del L by del Qj equal to 0, then the second equation Qj equal to minus del V by del Qj is um, yes, we have obtained that we have that del L by del Qj equal to d by dt del L partial derivative of del L by with respect to the velocity, using the Lagrange's principle, and del L by del Qj equal to 0. We finally come to the equation number 9, which suggests that Pj equals to constant. Now we are remain to show the conservation of energy using symmetrical approach. Here it has a very interesting property that even under this symmetry, in case of symmetry, we need to constrain our assumption in order to show the conservation of energy with time, right? Here we assume that conservative system, we assume the system to be conservative, and the constraint which is imposed on the system is explicitly independent of time, and consequently the equation of transformation to generalized coordinate does not involve time explicitly, and thus uh, Lagrangian, sorry, uh, okay, the Lagrangian L equal to L Qj Q dot Z. Now taking the first derivative with respect to t, we have equation number 10, because L is the function of Qj and Q dot Z, so it takes the form 10. Now we use the Lagrange's equation of motion, and substitute the values, as clearly we have assumed that the system is conservative. The we have equation number 11 suggesting that the v is independent of velocity. Thus the equation 11 has d by dt del t by del q dot z. Now using equation 10 and 11, we do have next equation dl by dt. Substituting the value of 11 in equation 10, we have summation j d by dt q dot z pj, and and uh, and uh, and doing sim then bringing the summation part to the left hand, no, bringing the dl by dt in the right hand side, we do have dy dt summation j q dot j pj minus l equal to 0, which implies that summation j q dot j pj minus l equals to constant. Here we need to know the actual term, the actual physics behind this equation. So here we have simply substituted the value of summation j q dot j pj. Here here pj is the momentum, therefore mj q dot j is the value of pj, and mj q dot j is simply the twice the kinetic energy. Thus above equation reduces to 2t minus l equals to constant, t plus v equals to constant. What this corresponded is that if we assume that the system is conservative, and assume that the constant imposed on the system is explicitly independent of time, and the Lagrangian is independent of t, then that system, in that system, thus that system corresponds to the conservation of energy, where h is the Hamiltonian and represents the total energy of the system under certain circumstances. Now here we have limited our assumption to the time independent. So what happens if we assume that the Lagrange is in fact dependent upon time? So So the above equation must reduces to dH by dt equals to minus del L by del T, where H represents the summation j q dot j pj minus L. Here H is the energy function. If we assume that the L is independent of time, then H is in fact the total energy of the system. But if we do not limit our assumption and uh, constrain that assumption, then in fact it is an energy function and it will be conserved if and only if the Lagrangian of the system is explicitly independent of time. That we have already seen while deriving the conservation of energy. Thus, in general, H does not represent the total energy of the system, but is total energy under many circumstances, which is assumed that which is clearly given in the let the system be section. So, do I need to explain the double pendulum also, sir? Hello.
Okay, go on, continue.
Okay, sir.
Okay.
Well, now we are going to talk about the equation of motion of double pendulum using Lagrangian approach. Here, double pendulum means we do have a two uh, two bob of masses m1 and m2, and they are and they are connected with each that m1 and m2 is connected with m1 with length l2, and m1 is connected with the point of oscillation by length l1. Now we are here to explain the equation of motion of these bobs using Lagrangian approach. We consider the motion of double pendulum in Cartesian coordinate system as shown in figure alongside. Here we assume that the point of oscillation represents the origin. Okay, then if it represents the origin, then clearly from the figure x1 equal to L1 sine theta 1, where x1 and x2 represents the position of bob m1, and x1 and y1 represents the position of bob 1 m1, and x2 and y2 represents the position of bob m2 there. And then x2 equals to L1 sine theta 1 plus L2 sine theta 2, y1 equal to minus L1 cos theta 1, y2 equals to minus L1. Here a minus came because we assume that the point is origin, right? Then below that origin, the values of y needs to be negative. And on differentiating the above equations, we do have uh, L1 cos theta 1 theta dot 1. Here the change in length is obvious. There is no change in length. Therefore, we have simply taken the derivative of theta 1. And similarly, we have taken the derivative of x dot 2 and y1 dot and y dot 2. And clearly, it is a two-dimensional problem. Therefore, the total kinetic energy must be equal to the half m1 x1 dot square plus y1 dot square plus half this is the energy of both bobs, half m2 x2 dot square plus y2 dot square. And substituting the above values, we finally come to equation number 15. Now the potential energy is simply uh, given by m1 gy1 plus m2 gy2. Here we have substituted the value of y1 and y2 and have a equation number 16. Here I have not shown the detailed mathematics because it would take a long form. Therefore, I have only written the final equations, and I'm sorry for that. And if you want the detailed equations, I can provide you the notes. The Lagrangian of the system is given by L equal to T minus B, and now we substituted the value of 15 and 16 in the L equal to T minus B, and we have equation number 17. Here clearly the theta 1 and theta 2 are the generalized coordinates, because L1 and L2 remains invariant under the motion of these bobs because they are constant. Therefore, what we need to specify the total configuration of the system is simply the angle theta 1 and theta 2. Therefore, we need to obtain the Lagrange's equation of motion for theta 1 and theta 2, and is given by equation number 18 and 19. And for theta 1 and theta 2, d by dt, this might be quite small in font, right? D by dt del L by del theta dot 1, and we have equation number 20, del L by del theta 1, which is equation number 21, and similarly for theta 2, d by dt del L by del theta dot 2, equation number 22, and equation number 23. Now we substitute these values in the Lagrange's equation which we have stated earlier, and we do have equation number 24 and 25. This equation number 24 and 25 represents the Lagrange, represents the actual motion of the system, actual equation of the motion of the double pendulum. And here is a very interesting property, that that the motion of the double pendulum, that if we track the motion of the double pendulum and we simulate it using different coding, then we can not easily we see that this equation in fact represents the chaotic motion. That means it is a very random, it is highly subjected to the initial condition, which we can easily see from the equation number 24 and 25, because it has a very long term. It considers both the theta 1 first and second derivative and even other equations, and this effect is somehow, this even so give emphasis to the butterfly effect, right? We have already known butterfly effect, that if butterfly changes its if it what do you call यदि बटरफ्लाईले चाहिँ आफ्नो प्वाखलाई चाहिँ मजाले फरफरायो भने चाहिँ एउटा ठाउँमा फरफरायो भने त्यसले गर्दा चाहिँ कुनै ठाउँमा हुर्केन आउन सक्छ भन्ने एउटा इफेक्ट छ नि। भन्न खोजेको अर्थ त्यसको एकदम के हाईली सेन्सिटिभ, एकदम सेन्सिटिभ सिस्टम रहेछ यो हैन। इफ वी change if we really change the its initial condition, then its equation vastly differ as compared to its previous motion. Thus equation 24 and 25 give the required equation of motion for the double pendulum. Thank you.